Saxon Algebra 2, lesson 66. It's a two-topic lesson today. And John proposes that we cover a topic called signs of fraction first. I am going to overrule him. I think the second topic is the one I want to put into your brain when it's most fresh. And so we're going to save signs of fractions for later. 30, 60, 90 triangles. That's what I want to talk about first. Okay. When we have used trig functions up till now, what we have learned is that you make a ratio of two of the sides, and then that has a relationship with the size of the angle, right? The degrees and that number. We see it first as a fraction, but we can turn it into a decimal. There's a relationship between those two things, and our calculator knows all the details, right? Calculators can help us connect the fraction, expressed as a decimal, to the degrees, and we can go back and forth if we can just figure out how to push the right buttons. Well, here's the thing. There are two very special triangles. One of them is a triangle that has a 30-degree, a 60-degree, and a 90-degree angle, right? Those are the three angles. We're going to memorize the fractions for those triangles so that we don't always have to use a calculator. It's good news, okay? We're going to get really familiar with this triangle. You're going to memorize it. You're going to be able to draw it at the snap of a finger. And it's going to make our trig lives smoother and easier because we don't have to be calculating with the calculator. And also the numbers are just going to be smaller and cuter and more even. So what I'm going to do is I'm going to teach you how to draw this triangle so that you can memorize it without really having to memorize it. You know, if you can recreate it, you don't have to memorize it. So what I want you to do is I want you to start. We're going to do it right now. We're going to draw a triangle that looks like a backwards play button on your TV or your Xbox or whatever. Mine's not perfect, but it's a backwards facing equilateral triangle. All three sides are the same, even if they don't look it. And we're going to call them each 2. I'll explain why we didn't just go 1, 1, 1 in a minute, but we're doing 2 is the length of each side. Now, if it's an equilateral triangle, I also know that the angles must be the same. And so each one of those is 60 degrees, right? So that we're starting just by drawing a really simple equilateral triangle and 2 for the sides instead of 1. We're making it as simple as possible, but we do have to make those 2. Now, what we're going to do is we're going to cut it in half right along here. Okay? And I'm going to draw this new triangle right over here so that we can see it a little bit better. All right, so let's see what we did. When we chopped it in half, we created a right angle right there, didn't we? Okay. This angle came over exactly the same. Nothing's changed. This angle got cut in half. So what was a 60 degree is now a 30 degree. Oh, look what we've got. 30, 60, 90, 30, 60, 90. This is the triangle we're interested in. Okay, so now we want to know the sides as well. We figured out the angles. Now we need to figure out the sides. This side was unchanged when we cut it, isn't it? This is still 2. This side used to be 2, but we cut it in half, so this is now 1. That's why I chose the number 2 in the first place, is because I knew I was going to cut one side in half, and I didn't want this to be 1/2, so I made the whole length 2 so that when I cut it in half, it would be 1. All right, that was really easy, finding the 2 and then the 1. This is the only side that is a little bit confusing, and we're going to call it X, but we know that a squared plus b squared equals c squared, right? That's Pythagorean. So we're going to call it x squared plus 1 squared equals 2 squared. Okay, x squared, this is 1. 1 squared is 1. And then we're going to subtract 1 from both sides. X squared equals 3. And then we'll take the square root. So this equals the square root of 3. That is the only number on this whole triangles program of angles and sides. This is the only one that's tricky, but you can easily recalculate it and you'll memorize it, I promise you, because you'll know 1, 2, and then 3 is the next number, but it's square root of 3. This is what we're going to memorize. And in a minute, we're going to do a few problems that will show you how and why that's useful. All right? If you just try to memorize this, it's not that hard, but it's a little tricky. If you memorize this process of the equilateral triangle, chopping it, and then Pythagoreaning it to that, you'll remember it right now. I promise you could do it right now. You don't have to, but I think you could. All right? Now, what this gives us is if we're standing here at this 30-degree angle marker, this gives us opposite, adjacent, and hypotenuse, and we can calculate those fractions. We've got the degrees, and we'd have all of the fractions for all 3 trig functions. Not only that, but if we reorient ourselves to the 60-degree angle, which for me, I usually redraw it the other way, so the 60 degrees down here, we can also do 60 degrees opposite, adjacent, and hypotenuse. So this is 2 angles built into one triangle that give us lots of fun little trig functions. So let's practice doing those right now. I'm just thinking of how I want to do this on my page. I think I'm going to go to the next page, and I'm going to draw this triangle again at the top. I'm not going to go through the whole well, I will. Okay, I know the triangle looks like this. Here, I'm going to draw 2 of them. This is the way I drew it last time. 30 degrees, this is the one that got chopped in half. That's the new right angle. This is the old angle that was untouched. Now with the sides, this is the one that was untouched. This is the one that got cut in half. And then that's the new one. Over here, I'm going to draw the triangle, only I'm going to flip it. Okay, this might be a little mind-bendy for you, but I'm going to take this corner and bring it down here and flip it over. The corner's still there. The 60-degree angle's now here, and the 30 is up there. Now, carefully, I'm going to transfer the sides. The short leg is 1. The long leg is square root of 3. The hypotenuse is still 2. Do you see what I did? I just picked it up and flipped it over. Now we're going to calculate the trig functions. For each of these triangles, okay? We'll have the sine, the cosine, I'm just skipping some spaces so you'll be able to see, and the tangent. First we'll do it of 30 degrees, because that's how this triangle is oriented. So we're standing here, and let's go through them. Oscar had a hold over Arthur. Make sure that you have this memorized by now. It needs to be something you can rattle off. Oscar had a hold over Arthur. You need to be able to rattle that off. If I, walked into your bedroom in the middle of the night and laid my hand on your shoulder and said, tell me the trig functions, you could rattle that off. Okay? Not that I'm going to do that because that would be extremely creepy. Okay, so here we are, 30 degrees. We need the opposite. The opposite is 1. The hypotenuse is 2. So here we are. We're human calculators. The sine of 30 degrees is 1/2. We don't need the calculator to tell us that. We just know. Okay, the cosine. The adjacent is square root of 3 over the hypotenuse is 2. See how I'm just pulling? I can do this. This is the hypotenuse. This is the adjacent, and this is the opposite. All right, so I'm just filling in the code. Tangent, opposite, 1 over adjacent, square root of 3. Okay, and then we often like to rationalize this top and bottom. So it would be the square root of 3 over 3. Okay, you don't have to memorize this because if you know the triangles, you can recreate this anytime you want. Now we're going to switch perspectives and go over here to the 60-degree triangle, and we're going to do the same thing. The sine of 60 degrees, I'm not going to rewrite the ratios because we can just look there. The sine of 60 degrees is, okay, let's do this, adjacent, opposite, hypotenuse. The sine is square root of 3 over 2. The cosine of 60 degrees is adjacent over 2. And then the tangent of 60 degrees, opposite over adjacent is 1. Or this could be simplified to just square root of 3. Look at that. We're human calculators. We don't need the calculator to give us trig functions for these angles anymore. We've got them right here. Notice there's an interesting pattern here. The sine of 30 degrees is equal to the cosine of 60 degrees. They're both 1/2. And the sine of 60 degrees is equal to the cosine of 30 degrees. They're both square root of 3 over 2. And the tangent of 30 degrees, if you look at this and compare it to this, the unsimplified forms, they're reciprocals of each other. That's interesting, isn't it? I mean, it's interesting to me. I don't know how much you care. We'll come back to that at a later date and talk a little bit more about that. The main thing I want you to do now is to see that when you memorized how to make one triangle, you actually memorized how to make two, and that gives us two sets of trig functions that we can now figure out just using our little picture. We don't know we don't need the calculator to do any of these calculations, which is great fun. So let's now work a couple problems. Let's see, how many are there? Just one. We're going to work a couple problems to see how this works. And we'll be using these a ton. The advanced algebra kids use them all the time. So we'll be using these triangles. They're at the heart of what trigonometry is all about. All right, let's see if we can do that reference triangle again, all right? We imagine that it was the full, I'm going to draw the full thing again. Backwards play button. 60, 60, 60, those are the degrees, and 2, 2, 2. We chop it in half. Oh my gosh, look how bad that is. And we bring it over. It's okay. You know what I mean. So it's okay if my triangle's really lopsided. This is the same. This turned into a 90-degree angle. This got cut in half, so that's 30 degrees. This number stays the same. This side got cut in half, so now it's just 1, 1, 2, square root of 3. Okay, this is the triangle we're going to need for the problem. This is called, just so you know, we call this a 30, 60, 90 reference triangle. I believe that's the way John refers to it. In the problems, he'll tell you to use a 30, 60, 90 reference triangle. I'm trying to find where he has the problems. No, he doesn't even say that. But that's what that's called. All right, I'm going to puffy cloud of knowledge it. Make sure you get this in your notes. Okay, example 66.3. John gives us a triangle and he gives us that angle and he tells us that, and then he says this is 5 and this is x and this is y. And he wants us to use similar triangles to find x and y. Okay, what does he mean by that? What he means is he wants us to recognize that this is the 30, 60, 90 triangle. He didn't write the 30 here, but we can put it there. It has to be. These have to add up to 180. He wants us to compare this to our reference triangle and then use proportions to solve. Oh, okay. So I'm going to draw our reference triangle. Now, this has a hypotenuse of 5. Our reference triangle has a hypotenuse of 2. So ours is going to be a little bit smaller, and I'm going to draw it that way, but it's not a big deal. You could make it any size you want. So ours is going to look like this. I'm going to draw it. Remember how on this last page, I drew it first with the 30-degree angle down, and then I drew it with the 60-degree angle. I'm going to draw it this way because I want it to compare to the other triangle. So I can look at this and get my bearing straight. This is my 60-degree. This is my 30-degree. Hypotenuse is 2. Short leg is 1. The short leg is the one there now. And then long leg is square root of 3. All right, now I'm just going to use proportions to solve this. Here's my anchor proportion, right? Using the hypotenuses, the hypoteni. So 5 over 2, going from left to right. 5 over 2 equals, let's do y first. Y is a little bit easier. Let's do x, because that's alphabetical. Sorry, I can't make up my mind. 5 over 2 equals x over square root of 3. See, we're just using proportions like we've done a billion times. And then we'll cross multiply, and we'll get 5 times the square root of 3 equals 2x. And then we'll divide by 2, and we get x equals 5 times the square root of 3 over 2. Now, is that a cute, attractive answer that you'd want to take home and play video games with? No, that's ugly, but it's correct. And we could easily grab a calculator and find that square root of 3, multiply it by 5 and divide it by 2. We could turn it into a decimal number really easily. But this is a perfectly acceptable answer, and we're not going to worry about changing its shape. That's lovely. We love it. Now we're going to do the same thing to solve for y. I'm going to do that in this area. 5 over 2 is still our anchor proportion, and this time we'll have y over 1. And the beauty of this one is that we can just ignore the 1, and we can say y equals 5 over 2. Yay, that's also the right answer. This is a great example of how easy these problems can become when we don't have to worry about grabbing our calculator and pushing a bunch of weirdo buttons, all right? That's what the 30, 60, 90 triangle is good for. It allows us to calculate trig values. As long as they're on these angles, we can calculate trig angles by hand. Oh my gosh, how much fun is that? Okay, that's really important. I'm glad we put that in your brain first. Now we're going to go back to the first topic, which again is called signs of fractions. And this is a fairly straightforward idea that can help you in certain kinds of problems. And I'm just going to jump right to the chase. There's only 2 examples here. Example 66.1. Add what we have here is a pair of fractions that we're supposed to be adding. I'm going to write that down. That's the instructions John gave us. All right. But as you can see, the problem is that the denominators don't match. And as we look at them, we could multiply, we could make a least common multiple of this quantity times this quantity, but that would just be a giant mess. What we notice is that this is the same as this, except both of the signs are different, right? Positive x, minus x, negative 3, positive 3. It's just the signs that are off. So is there a way to fix that, change that, so that we don't have to go through that long drawn out least common multiple process? The happy answer is yes. What we want to do is multiply the bottom of this fraction, called the denominator, by -1. That will change that to positive and that to negative, and everything will match and we'll be happy. Fabulous. But of course, we all know if you do it to the bottom, you got to do it to the top. So we're going to have to multiply that by -1 as well. And we're going to have to pay very careful attention to this. Okay, so let's go one step at a time. Let's start by multiplying these. So the first part stays the same. The minus sign stays the same. But I'm going to do that. And we're going to get minus 7a over, and then I'll distribute these, positive x minus 3. We did it. The denominators match. They look really good now, right? The final step, though, is we see we have minus, minus. We don't want that. So we're going to combine these two. Right? So as soon as you see the minus sign out there and then you make the decision to multiply by -1, just remind yourself you're going to have to watch that and give yourself one more step. So our final answer is 1 over x minus 3 plus 7a over x minus 3. Well, technically that's not the final answer because now we can squish it and we get 1 plus 7a over x minus 3. We would have gotten the same answer if we would have missed the memo and just made those into the least common. Oh, it would have been a mess. We didn't want to do that. All right, so in certain circumstances, we'll recognize that we can use this multiply top and bottom by -1 trick, and it will help us deal with this. Of course, it'd be quite a coincidence that our denominators are so close and yet so far, but John's going to set some problems like that up for us. So we shall look forward to solving them. And I just have one more that's like that. Example 66.2. And I'll copy. What John did this time is he reversed the order, right? X minus 3, 3 minus x, positive x minus 3, positive 3 minus x. He reversed the order so it looks a little different, but again, we can train our eyes to catch these situations. Again, we look at this, we puzzle over it. Yeah, we could do a least common multiple of quantity x minus 3 times quantity 3 minus x. We'd get the same answer, but that's a headache and a nuisance. We don't want to do it. So we go, okay, let's use our old -1 trick. Typically, John sets these problems up so that it makes a little bit more logic to change the second one, but we could change the first one. We could make them both have 3 over x on the bottom, or 3 minus x rather. We could change this one so it looked like this, rather than changing this one so it looks like that. I hope that makes sense. But I like that one better. That's the way John usually sets it up, is he gives us what looks normal first, and then he gives us a weirdo in the second one. Again, we can have 2 weirdos. There's no shame in that game, but I prefer to do that. All right, both of these are quantities, so we're going to have to be careful that we're changing the signs on both pieces. So I'm going to draw my little whoop-de-doops because that makes me feel better. Copying. This thing is unchanged. Okay, ready? It's going to be, I'm going to put them in parentheses because again, I'm being very careful with my signs. Here we have a plus sign, so I still have to be careful with that. We're going to keep an eye on it. Okay, so it's going to become minus 2x plus 3 over, I'm going to write them in the opposite order. There's my positive x, and then now it's a minus 3. Okay, these match. right? Everything's good. Now, do I need the parentheses up here? What happened? What does this plus sign do? Does it change this in any way? No, it does not. So I can ignore these and simply see this as 4x plus 5 minus 2x plus 3 all over x minus 3, right? The denominators match. This is a plus, so I don't have to worry about changing any signs, and I can just write them all in a clump. And now I just want to add like terms up top. 4x minus 2x gives me 2x. 5 plus 3 is 8. And then my denominator is a happy x minus 3. Yay. All right, so this multiplying top and bottom by -1 is a fun little trick we can use if we ever want to change the signs, specifically in our denominators, but it'll change the numerator too, right? But if we're ever looking to match them and we're close but no cigaring it, go ahead and make that change. Guess what? 66 is over. It's so satisfying to cross off those lessons. I know you have to do the homework and I don't, but man, I just get great satisfaction of ticking them off as well. So I can imagine how you feel. If you don't have a checklist like this and you would like one, just email me and I can send you a copy of this document that my local students use to check off and to know when the tests are coming. Even if you're not on the same calendar date as me, but you just want a checklist, let me know. I will hook you up. Okay, thank you. Goodbye.